Okay, welcome back to Uniform Circular Motion Part 3. Okay, the last couple of sessions we've looked at uniform circular motion and centripetal acceleration, centripetal force. And we've also looked at how uniform circular motion and centripetal force would apply in a horizontal circle. In other words, an object moving in a circular motion horizontally. Well, this time we're going to look at what happens when the circle is in a vertical direction. Because when it's in a vertical direction, remember, force of gravity comes into account. Okay, force of gravity, things like the normal force can now be included. Tension in a string can be included. And we're going to look at examples that include all of those things now in just a second. So, when we talk about vertical circles, remember, so far we've talked about horizontal only. And when we're moving horizontally, it looks like this. Okay, force of gravity is downwards, but centripetal force, remember, is towards the center. So the force of gravity is ignored in that case because gravity is not a horizontal force. So it's perpendicular to the actual force, so therefore it doesn't affect it. But in a vertical plane, when we move vertically, then the force of gravity does affect it, very much so. Okay, force of gravity is always pulling down. Now centripetal force, this is not a free body diagram obviously because centripetal force doesn't belong in a free body diagram, but just there to show you the direction of that vector. So the centripetal force and the force of gravity are in a different direction at the bottom of the circle, but in the same direction at the top. Now obviously there's going to be another force here as well, because at the bottom of the circle it would be impossible for force of gravity to be down and centripetal force to be up, because how can the net force be up if the only force there was down? That can't happen. So obviously there's got to be another force here. And that other force is usually one of two things, either tension, like tension in a string if that was a ball attached to a string, or it could be normal force. And we're going to look at both of those. So remember that Fc is F net. And we can find F net by looking at the sum of the forces. So let's assume that this is a ball tied to a string. So at the top of the path, the net force, okay, the net force would be Fc, right, because net force in a circle is always Fc, which is the sum of the forces, would be tension at the top plus force of gravity. Now, technically, all of those forces are down. So I'm going to do this. Because all of those forces are down, I'm going to say that every one of these is a negative. It's a negative Fc, it's a negative tension, and a negative Fg. But because they're all negative, I can just drop the negative signs. I can divide everything by -1 and it's all good. The negative signs are all gone. So I'm left with Fc equals tension at the top plus Fg. Now if I move the Fg over here with the Fc, I end up with tension at the top equals Fc minus Fg. Another way to write that, and some of you may actually have this little expression memorized, would be mv squared over r minus mg. Okay? That is always the tension at the top for these situations when you have a ball tied to a string. That's always the tension at the top. At the bottom of the path, Fc is up, so Fc is positive. Tension is up, so tension is positive, but Fg is down, so it's negative, which is exactly what we've got here. Now that means that Fc equals tension at the bottom minus force of gravity. If I rearrange that one, I get this expression, which is the same thing as saying this. It's the same thing as saying this, equals mv squared over r plus mg. So now you should be able to tell just by looking at those two expressions where the tension is biggest. The tension in that string is always going to be bigger at the bottom of the circle, because at the bottom of the circle it's Fc plus Fg. But at the top of the circle, the weight actually reduces the tension in the string. Because the centripetal force, remember, doesn't change. It depends on the velocity and the radius, which is not changing here, because this is uniform circular motion. The speed is not changing. Velocity is changing direction, but not magnitude. So if you were asked, for example, where would the tension be the greatest? Always at the bottom. Where would the string be most likely to break? Always at the bottom. Where would the tension most likely be zero? Always at the top. Okay, so those types of things do come up from time to time, so keep them in mind. The tension at the top of the circle is always the smallest, and the tension at the bottom is always the largest. Okay, always the largest. So, with that in mind, let's look at some examples. We've got a 1.20 kilogram ball on a string is swung at a speed of 3.57 meters per second in a vertical circle with a radius of 1.10 meters. What is the tension in the string at the top of the circle? Okay, so what I'll do very quickly is I'll just draw a diagram. At the top of the circle, okay, here's the string. Center of the circle is down here. So force of gravity is down. All right, the tension is down, and Fc is down. So Fc, which is net force, is negative because it's down. The tension is negative because it's down, and Fg is negative because it's down. If I rearrange that, I get this expression. T equals, bring the T over, okay, I would have, okay, at the top of the circle, I would have Fc minus Fg. So in other words, I would have tension equals mv squared over r minus m times g. Okay, it's always the same expression, like I said. So if you memorize that expression, plug all your numbers in, that happens to equal 2.1. There it is right there. Okay. These expressions, by the way, these two right here, one of those is Fc, the other one is Fg, okay, and this one here is when you add the two together instead of subtracting. So every one of those numbers is a possible answer for this, so you really got to be careful. You really got to be careful. All right, let's try this one. We got a roller coaster car with a mass m. It doesn't tell you what the mass is. In fact, it actually looks like an automobile. But anyway, it's on a track that forms a circular loop with a radius of r in a vertical plane. Okay, radius of r. If the car is just barely going to maintain contact with the track, what expression represents the minimum speed at the top of the loop? Well, think about the forces acting on the car at the top. Here's the car at the top. I've got gravity pulling down. Normally, I've got a normal force. Now, my normal force would be down in this case, and it's downwards because the surface is above the car, right? It's upside down. So, Fn, in this case, because we're talking about minimum speed, that tells me that Fn is equal to 0. At the bare minimum speed, that's when the normal force goes to 0. That's when the car just barely touches the track. So my expression, that's the same thing as tension, really, right? So my expression ends up being F net is only equal to Fg, right? The Fn is gone. I don't need it anymore. So Fc equals Fg, which means mv squared over r equals m times g. I can cancel out my masses, and I'm left with this expression. V squared equals r times g, which means V equals the square root of r times g, which obviously is this expression right here. Now I got another way of writing that one, just like the other one where I said the square root of rug. Well, this one, I like to write it this way. Square root of gr, the square root of gr. Okay, and if you think of that, I guarantee you're going to remember it. Square root of gr. And the square root of GER is kind of like the square root of RUG, but the square root of GER only applies to vertical circles. The square root of RUG only applied to horizontal circles. Okay? So that square root of RUG, that gave you the maximum speed in a horizontal circle where the only force keeping the car moving in a circle was friction. And this one gives you the minimum speed in a vertical circle when there's no normal force or no tension in the string if it's attached to a string, etc., etc. So that's another one that's very useful to remember. V equals the square root of GER. Okay, so keep that in mind. Sounds odd, but it's a great way to remember it. Trust me. Let's try the next question. This time we got a car driving into the bottom of a small valley. So you got a dip in the road. We want to know what is the normal force acting on the car. So in this case, the normal force is up. The force of gravity is down. Okay, so that's kind of like the tension ones, isn't it? So I can just write it like this. I can say F net is equal to, in this case, F net is equal to FC. And FC is upwards because the center of the circle is up here. Fn is also upwards because it's pointing up. And Fg is minus because it's pointing down. So if I want to find Fn, I just move the Fg over. So I would have Fn is equal to Fc plus Fg. Or in other words, mv squared over r plus m times g. Exactly the same expression that we had for tension at the bottom, isn't it? It's exactly the same expression that we use for tension at the bottom of a circle. Normal force and tension in these situations are actually going to be interchangeable. They're actually interchangeable. So we plug in those values that we have. Here's the mass. Here's the speed. Here's the radius. Plug those in there. G equals 9.80. And you will get, as your answer, 31,445 newtons of force. Now, that's not there as such, but if we change it into scientific notation with 2 sig figs, it would be that answer right there. So there's the correct answer. And again, that is where the normal force would be the maximum, the absolute maximum. Let's try another one. Similar situation. This time we've got a pilot in a plane traveling at a speed of 2.50 times 10 to the 2 meters per second. In other words, 250 meters per second. And this pilot experiences a normal force of 7 times his weight at the bottom of a vertical dive. Well, right at the bottom, that's the same thing as tension at the bottom, right? So instead of tension equals, I'm going to say Fn equals Fc plus Fg. That's the expression. Same as T equals Fc plus Fg. Now, we want to know the radius of curvature of the dive. So I'm going to rearrange this a little bit. I'm going to say that's the same thing as Fc equals Fn minus Fg. So mv squared over r equals, now, Fn. I don't know what Fn is, but I do know that the normal force is 7 times his weight. In other words, 7 times mg. Take away Fg, which is also mg, 1 mg. Now I can cancel out all my masses again, which is a good thing because there's no mass given for the plane or the pilot. So I do that, and I end up with v squared over r equals 7 take away 1 is 6g. 6g. So that means that if I want to know what r equals, I just rearrange that equation, and I get v squared over 6 times g. So I've got my 250 meters per second squared divided by 6 times 9.80. And if I do that, I will get 1,063, which rounds off to 1,060 meters when I put 3 significant digits there. And I'm allowed to use 3 because the only number I was given in that question had 3. So there's the answer. So you don't seem to be given a lot of information, but there is enough information there to solve that question. Okay, so that's another one that would be considered to be a level 3 question. That's another level 3 right there. Let's move on to another one. This one here. Now we've got a pail of water being swung in a vertical circle with a radius of 1.3 meters. We want to know the minimum speed at the top that keeps the water from spilling. Well, at the minimum speed, the tension in that string would become 0. We want to know at what speed would the tension be exactly 0. So in other words, Fc is equal to Fg. And that's where we get this one again. Remember, V equals the square root of GR. That is the square root of 9.80 is G. The R is 1.3. We multiply those together and take the square root. Here's what you get. 3.6. Right there. By the way, if you forget to take the square root, you get that answer right there. That's what you get if you forgot the square root. If you forget the square root. So that answer's there, so don't forget the square root. Remember, square root of GR. That one comes in handy, trust me. Okay, let's look at some long answer or constructed response questions. And again, these are fairly common. Okay, this time it doesn't say anything about minimum speed, but it does ask you to calculate the normal force. Well, at the top, remember I've got negative Fc because centripetal force is down, negative Fn because the normal force is also pointing down because the cart is upside down, minus Fg. So if I rearrange that, I would get Fn equals Fc minus Fg. That would be the expression for normal force. Same thing as tension. Tension will be interchangeable with that, like I said before. So that means we've got mv squared over r. So let me show you what the solution to this one is. Okay, so there's what they did. Fn equals Fc minus Fg. So a half mark for remembering that equation. And then for changing it into mv squared over r minus mg. Plug your numbers in the right place, get a mark for doing that, and then for actually getting the answer, another half a mark. So that question was 2 marks in total. And the answer is 4.10 multiplied by 10 to the 3. In other words, 4,100 newtons. But because, just look, if you look at the numbers here, this guy here, 3 significant digits. This guy right here, 3 significant digits. The radius right here, 3 significant digits. So in other words, your answer also needed to have 3 significant digits. Okay, so those types of questions, always put in the right significant digits and the right units, because you never know which question on that exam is going to be actually looking for that. You don't know. So do it all the time just to be safe. And like I said before, if you can't figure out how to do the answer, at least write something down with the right significant digits and the right units, and you never know. You never know. Let's try this one. This time we're asked for the minimum speed at the top required to keep the car on the track. Remember that? We can do it this way. V equals the square root of GR. We can do it that way if we want. Okay, so Fn equals 0 at the minimum speed, right? That's why that works. So that's why we get this expression. V equals the square root of GR. So just by writing that down, by this marking scheme, because in order to get that, you had to first of all assume that this was true, and then that this was true, and this was true, so therefore you end up with this. So you get half the marks for that question just for doing that, believe it or not. So memorize that expression. It's going to come in handy. Then you plug your numbers in. You got your answer. And the answer is 6.6 meters per second is your minimum speed. Any slower than that, the cart's going to fall off. Now you'll notice that for these speeds, the mass doesn't matter, does it? Which is a good thing when you think about it, because whether that roller coaster runs empty or full, the minimum speed doesn't change. Which is good to know if you're riding on a roller coaster and sometimes it's full, other times it might not be full. But it doesn't matter because the mass doesn't affect the outcome. That speed is still going to be the same regardless. So that's good to know. Next question. Now, this one is a little bit different. This one's a little bit different. You're again asked to find the normal force, but this time the car is not upside down. The car is actually on the top of a really round hill. So for this particular one, here's what the free body diagram would look like. Force of gravity down and normal force upwards this time, not downwards. And that's very important. That's very important. Because now we get this expression. Remember before we had FC equaled something different. Okay? Before it was all negatives and we ended up with a plus sign. This time we get a minus sign. Now that's significant. That's significant. The way I would have written that is I would have said FC negative, because the center of the circle is down, equals Fn positive minus Fg. So what they've done is they've changed all the signs and they said Fc equals Mg minus Fn. They changed all the signs around. They divided everything by -1. Okay? So that's a slightly different expression. So you've got to be careful. Okay, so there's what you plug in. You rearrange that. You get Fn equals Mg minus Fc. Normally at the top, it's actually the other way around, Fc minus Mg. So what's going to happen here, is you're going to get the opposite sign. So anyway, there's the answer. It works out to be positive because Fn is upwards. If you had done it so it was upside down, you would have ended up with Fn negative. Okay, you would have gotten a negative answer because Fn was down. But anyway, Fn is 4,980 newtons. But you had to be careful there, because if you did it the other way around, you would have got the wrong sign. And then you would have known something was up, or something was down, or something was wrong, I should say. Because up and down are the directions there. All right, so that one is a little bit different, like I said. Because the car is on the outside of the circle, right, up here instead of down here, that changes one of the directions. So you really got to be on your toes sometimes for that stuff. Next one. What would be the maximum speed that would allow the car to stay on the road? The maximum car that would allow the car to stay on the road. Remember, as the car goes faster and faster, it would start to lift off the road. And if you've ever gone over a bump fairly fast, the top of a hill fast, you can actually feel your car lift a little bit. So in this particular case, again, Fn equals 0. Okay, that's the key to this one. Fn equals 0. So the markers for this particular exam said that was worth 1 mark just for recognizing that at that maximum speed, now usually it's minimum speed, isn't it? But usually the car is upside down, so it's a minimum speed before it starts to fall. Well, this time it's a maximum speed before it starts to lift off the road, but it's exactly the same type of situation. Because Fn equals 0, you can say mv squared over r equals mg, or in other words, v squared equals rg, or v equals the square root of GR. Remember that one? V equals the square root of GR. So you plug in those numbers, you get a maximum speed of 22 meters per second. Any faster than that, the car will begin to lift off the road. The car actually begins to lift up, go airborne. at those speeds. Anything above 22 meters per second, that would happen. Below, you still have a normal force. But as soon as you go above that, you end up with a negative normal force, which means the car is not even touching the road anymore. It actually starts to lift. Let's try another one. This one's a little bit different too. In an automatic clothes dryer, we got a hollow drum that moves the clothes around in a vertical circle, and you see the clothes will actually start to tumble around inside the dryer. So the dryer is designed so that the clothes tumble and do not simply stick to the drum as it rotates. If it rotated too fast, then the clothes would actually stick to the outside of the drum because there would be too much centripetal force. And if you've got one of those front-loading washers, if you look inside it while it's spinning, you'll actually notice that's what's happening. That's what's happening. The clothes actually sticks to the edges. But you don't want that to happen in a dryer because the clothes wouldn't dry properly. So the clothes is in a vertical drum with a diameter of this, a diameter. Now that's an important distinction because normally when we do these calculations we use radius. So we're going to have to change that diameter to a radius. So again, you've got to really read the questions carefully because sometimes they can be tricky. We want to know that what the speed would have to be for the drum to rotate so that a sweater with a mass of 0.425 kilograms would just begin to tumble. In other words, just begin to fall when it gets to the top. So in other words, at the top, Fn equals 0 again. Fn equals 0. So here's what we got. Fn equals Fc minus Fg, but Fn is 0. So in other words, Fc equals Fg, or mv squared over r equals mg. Okay, that's your key. You can cancel out, right? Cancel out your masses. They can go. And that leaves you with our old friend v equals the square root of GR. You plug in the values and you will get not a very fast speed. And if you've ever watched a dryer operating, that's not unusual for it to be moving fairly slowly. Like I said, if it moved too fast, the clothes wouldn't tumble. It would just stick to the sides of the dryer, and you take forever to get it dried properly. That's why clothes hung on the line dries faster, because it's waving in the wind. The more it moves around, the more wind there is. Number one, the harder it is to keep it on the line with clothespins, but number two, the faster it'll dry because it's moving around more. The more you can get it to move around, the more air you can get circulating around it, the faster it's going to dry. So that's why the clothes dryer is designed to do that. The washer spins fast because it wants to spin as much of the water out as possible. But you'll never get it dry like that. You'll never spin it fast enough to get all the water out. So that's why you need to use a dryer. Okay, so again, V equals the square root of GR, our old friend GR. Okay, like I said, remember that expression. That's a really useful one. Very useful. All right, one last example. This one gets at a little more understanding again. This kind of ties it all together. So we've got a stone that's tied to a string, and it's whirled around in a circle of radius 0.75 meters at a constant speed of 5 meters per second. In which of these situations would the string be most likely to break? In other words, in which of those three situations would the tension be the greatest? And the answer, of course, is when you are at the bottom of a vertical circle. That's where the tension is greatest. That's where the tension is greatest. And here's the reason for that. Take a look. For the horizontal one, because it's moving in a horizontal circle, Fc equals the tension, or tension equals Fc. So in other words, tension equals mv squared over r. Okay. Then, for the top of the vertical one, remember it was always Fc minus Fg because of the directions, right? And then at the bottom of the vertical, it was always Fc plus Fg. So you can see that this guy down here, he's the max. This one here is the minimum. And this guy right here, the horizontal circle, that's the median. There are actually three different tensions in each of those situations. even though it's all uniform circular motion, because of the forces that are causing that centripetal force, the tension is different in every single case. But we want to know where the string is most likely to break. That would be where the tension is at a maximum. And that's that guy right there. The string most likely breaks where the tension is greatest, and that happens to be at the bottom of a vertical circle. That question was worth 3 marks. For most of you, that should have been a fairly easy 3 marks. Okay, that's not an overly difficult question. But it's a level 3 one, because you really got to get at the understanding. You really need to understand what centripetal force is in order to answer that question. Okay, so that brings us to the end of vertical circles. So we've done a large number of examples. We've covered pretty much all the different types of questions that have been asked on recent public exams in those. Okay, so the only topic left now in uniform circular motion would be banked turns. Banked turns. So what happens there is, instead of the turn, like in the horizontal circle, instead of the turn being flat and relying on friction to get around a turn, sometimes turns are banked. And if you look at racetracks, is where that's really strongly evidenced. So that's what our next topic, topic 12, will involve. So again, good luck with your studying, work hard, and tune in for more lessons.